welcome back. Let's talk about exact equations. These are a little more difficult to grasp at first, but they're actually one of the easiest types of equations to solve. Because they only look a certain way, right? Okay. So exact equations. So let's recall, the differential form of an ordinary differential equation is, this is a first order, I should say. First order ODE is some function of x and y, who cares what it is, times the dx differential, plus some function of x and y times the dy differential equals 0, right? This is called the differential form of a differential equation. So here's a definition for you. If we have z, which is a function of x and y, so you've probably seen this in Cal 3 before, right? We'll have z is a function of two other variables. This will be our third variable. If this is a function of two variables with continuous first partial derivatives, then it's differential, right? We say the differential of z, which is dz, right? This is the differential of z. The differential of z is equal to the differential of f, since z is equal to f. And the differential of f is defined as the partial derivative of f with respect to x, dx, plus the partial derivative of f with respect to y, dy. This is the best thing, or I guess this is like the closest thing we have to a derivative in multivariable calculus, right? The differential. The differential. And specifically, if f is equal to a constant, right? If z equals a constant, if f is equal to a constant, then taking the differential on both sides, you get the differential of f on the left-hand side, and on the right-hand side, the differential of a constant is 0. Right, so on the left-hand side, we get this, and on the right-hand side, we get 0. And if we look up at what's called the differential form of an ODE, right, it looks really similar. But in this case, m is playing the role of partial f, partial x, and n is playing this role of partial f, partial y. And that's kind of the idea, right? So the idea is, if you see an equation like this, it could be the case, it might be the case, it's not guaranteed, but it might be the case that this is the differential of some function equal to a constant. That's the idea. And in that case, that would be the solution, right? In that case, this f would be the solution to the differential equation. Or I guess this technically would be the solution. Okay, let's look at an example. Let's say f of xy is equal to xy, right? Let's say that's our function z. So z equals x times y. Then its differential, right? The differential of f, right? This is the differential of f, which is equal to the differential of x times y, is equal to partial derivative. So this right here, right? This is partial f partial x, which is y. And then this is partial f partial y, which is x. Dx, dy. Right, that's the differential of that function. So the question is, that I've already kind of hinted at this, right? When does a first order ODE in the differential form correspond to a differential of some function, right? When is that the case? Well, it's pretty easy to check. Here's a definition. An ODE of this form is exact if there is some function f such that the partial of f with respect to x is equal to m, and the partial of f with respect to y is equal to n. Right? In that case, if this is df dx and this is df dy, then we say that this is an exact equation. This is an exact equation. And in this case, the solution, right? The solution would be f of xy equals a constant. That would be the solution. Okay, that's great. But how do we actually solve these things? Right? How do we actually find this function f? Well, let m and n be continuous functions with continuous first partial derivatives. Then this guy is an exact equation, right? Which means there is some f such that m is the derivative of f with respect to x and n is the derivative of f with respect to y. This is exact if and only if the cross partials are equal, right? The cross partials are equal. Remember, this equals, so this is the derivative with respect to y of the derivative of f with respect to x. And this is the derivative with respect to x of the derivative of f with respect to y, right? If this is the case, then these cross partials should be equal, right? If you remember from Cal 3, the cross partials are equal. Or they should be. They should be. So, the point is this equation is exact if and only if this equality holds. Right? This equation is exact if and only if this equality holds. So, the first step to solving these differential equations is to check if they're exact. And to check if they're exact, we just check this condition. Right? And if this condition is satisfied, then we can use this relationship, right? This relationship on the side here to solve for f. To solve for f. Let's see how it works. Let's see how it works. Here we go. Solve the following differential equations. First one, 2xy dx plus x squared minus 1 dy equals 0. Now, our first question should be, what is m and what is n? I've already outlined it here, right? I've already underlined it. This is our function m, and this, technically including the plus sign, is our function n, right? If this was a minus sign, we would include that in n. That's all I'm saying. So this, I really should have underlined this is n, and this is m. Right, the thing in front of dx is m, and the thing in front of dy is m. The first question is this exact? Is this exact? Well, if we look back up, this equation is exact if and only if the partial of m with respect to y is equal to the partial of n with respect to x. Right? So the thing out front of the dx, you need to find its derivative dy. And the thing out front of the dy, you need to find its derivative dx. That's why I call it the cross partials. The cross partials. Well, we can check that pretty easy, right? Partial m, partial y is 2x, right? 2x. And partial n, partial x is also 2x. And since those are equal, this is an exact equation. Yes, this is exact. Yes, this is exact. Excuse me. Okay, so by the theorem then, there must be some function f such that the partial of f with respect to x is m, and the partial of f with respect to y is n. Right? Because it's an exact equation, there must be some function satisfying both of these differential equations. Both of these differential equations. Well, we can solve this one pretty easily, right? We just integrate both sides dx, partially dx. We just need to be careful because there could be some function of y tacked onto the end of this thing, right? Well, let me just do the example. Okay. So, since the partial of f with respect to x equals 2xy, then f should be the integral of this dx, right? F should be integral of this dx. Okay, when we integrate this dx, we get x squared y here, and then we tack on some function of y alone. Some function of y alone. Now, why do we do that? Because y is constant with respect to x, right? If you start here, if you call this f, right, f of x and y, and you take its partial derivative dx, this whole y term is going to go away because it doesn't have any x's in it, right? This term doesn't have any x's in it, it's all y's. When you take a partial dx, this whole term is going to disappear, and you're going to be left with this as the derivative. Right, so instead of adding a constant of integration, right, we're now adding a constant function of integration, basically. Because we're anti-differentiating partially. Oh, excuse me. Because we're anti-differentiating partially, we get this function of constant function of integration. Excuse me. Now, there's a lot of ways you can do this, right? What I like to do is I like to take this f, I like to take this new f, right? This one I just found, and take its derivative dy. Take its derivative dy. So I just integrated it dx, now I take its derivative dy, right? And that gives me this function. Right, if I take the derivative of this dy, the derivative of this dy is just x squared, and the derivative of g dy is g prime. And now I go back. So I have here an expression for partial f partial y, and I have here an expression for partial f partial y. Right, we see x squared minus 1 and x squared plus g prime of y, which must mean that g prime of y, right, sorry, g prime of y is negative 1, right? So since partial f partial y was equal to x squared minus 1 originally, right, that was all the way from up here. That was all the way from up here. That must mean that g prime of y, is equal to negative 1. G prime of y is equal to negative 1. So if I integrate this, this should be g of y. Should be g of y. G of y. So if I integrate this, both sides, dy, I get g of y equals negative 1. And that goes here, right? This goes here. And then I have an expression for f. And then I have an expression for f. Pardon me. So f of xy equals x squared y minus y, right? Because f of xy was supposed to be x squared y plus g of y, and I was looking for this constant, and I found it down here at the bottom. And so when I plug that in, I get this. Last step. We cannot forget. This is not what the solutions look like. This is just a function. Solutions to this differential equation look like this. F of xy equals a constant. F of xy equals a constant. Okay. It's complicated to explain, but once you've done it a few times, it's not too bad. Let me see if I can do this out pictorially. So up here we have f of x and y, right? Now we can take its derivative, dx, right? Partial x. And that should give us the function m. We can also take its derivative, partial y, and that should give us the function n. And if we take the derivative of this partial y, we should get m sub y, which should be equal to n sub x, which is the partial derivative of this dx. So the first step to solving these is to make sure that you get this equality, right? This is step one. Right, that's checking the theorem. If you get that the cross partials are equal, then it's exact, which means you can solve it. But how do you solve it? The way I do it is I start with m, right? Start here. I integrate dx, right? Integrate dx. Take m, integrate dx. You should get some expression for f, but that will involve a constant. And to solve for the constant, you then differentiate that thing you just found, dy, right? And compare it to n. Maybe this is an easier flow chart, right? So I start with m, right? I integrate that dx. That gives me like f of xy plus or minus some constant g of y. I then differentiate that partial y to get something that looks like n, right? Something that looks like n. And then I compare both sides to figure out what g prime of y is. This is much harder to explain than I thought it would be, but maybe doing some more examples would be the best thing. Okay, here's one that looks bad, but it's really not bad. It looks bad, but it's really not bad. So here we've got an equation. This is going to be my m function. This is going to be my n function, and it's in the differential form already. And our question is it exact? Is it exact? Well, in order to see if it's exact, we just have to check that the cross partials are equal, right? Check that the cross partials are equal. Since this is in front of dx, I'm going to take the derivative of this dy. And since this is in front of dy, I'm going to take the derivative of this dx. And you can see, if you take the derivative of this dy, you get 2e to the 2y. And then you get a product rule on this side. Derivative of the first, keep the second, is this term. And then derivative of the second is negative sine xy times x. And then the y hangs out up front, right? So derivative of this gives us this product. And the same thing for n, right? When you take the derivative here, you take the derivative here dx, you get 2e to the 2y, because this is times x. And then you take the derivative of this dx, you get a product rule again, right? Same product rule. And then when you take the derivative of this dx, you get 0, right? And since these two are equal to each other, right? This partial derivative and this partial derivative are equal to each other. That means this is exact. This is exact. So there is some function f. So there exists some function f such that partial f partial x is m and partial f partial y is n. Right? And that's what we're looking for. So again, I'm going to start with m, which is partial f partial x. Right? Start with m, which is partial f partial x, and that's this guy. And now I'm going to take m and I'm going to integrate it dx. If I integrate this dx, right, what happens? I kill off the derivatives. So I'm going to integrate this dx, right? This is the integral of m dx, which if we integrate this dx, we get an x e to the 2y. Integrate this dx, the y hangs out. integral of cosine xy. Integral of cosine is sine. Keep the inside. Times, we're integrating this dx, so we're going to multiply by 1 over y, right? That's this. And then, don't forget, tack on your constant of integration, right? Tack on your constant of integration. And I should mention, if you don't like the way I do this, right? If you don't like this method, there are other methods to solve these exact equations, and you should go look them up if you're struggling. Okay, so back to it. We've integrated m dx, and we've got this expression for f, right? Now I know what f is up to this constant of y. So what am I going to do? I'm going to differentiate this partial y and compare to n, which is supposed to equal partial f partial y, right? If I take the derivative of f dy, that should be the same as the derivative of f dy, right? And by comparing those two things, comparing n to whatever I get from this, should give me an expression for g prime of y. So let's do it. So since f equals this, its derivative with respect to y is equal to this. Right? Derivative dy, this doesn't have any y's in it, it hangs out. The 2 comes down, and we get e to the 2y again. Derivative here, dy, well, derivative of sine is cosine. Derivative of xy dy is just x, that's this. And then the derivative of g of y is g prime of y, dy. Now, here's an expression for partial f partial y, and also in itself should be an expression for partial f partial y. So what do? Since this differential equation is exact, this partial f partial y better equal n, which is this. And just by comparing, right, we can see that g prime of y is 2y. And then integrating this dy, we get g of y equals y squared. G of y equals y squared. Therefore, my function f, where are you? Right here. I just take g of y and I plug in y squared. Therefore, f is equal to this, but that's not the end, that's not the solution. To get the solution to the differential equation, you set this equal to a constant, right? So the solutions to the differential equation look like this. Okay. Another one. dy dx equals xy squared minus cosine x sine x divided by y times 1 minus x squared. Okay, that looks complicated. They've also given us an initial condition, which means we're going to be able to pin down the constant c, right? Whenever you're given an initial condition, that means you can find this constant. That means you can find that constant. This is not a linear function, right? And since so far we only know how to solve linear functions and exact equations, we better hope this is exact, right? We better hope this is exact. How can we figure it out? Well, we have to put it in its differential form, right? We need to put it in its differential form. So we're going to cross multiply. We're going to cross multiply here. So we get y times 1 minus x squared dy, and then we get xy squared minus cosine x sine x times dx, right? That's our almost differential form. And then we just got to swing this guy. Well, I guess it doesn't really matter. I like to keep a plus sign out front of the dx term. So I'm going to swing this term across this equal sign, right? Which means this is m and this is n. And the question is this an exact equation? Is this an exact equation? Well, it's exact if m sub y is equal to n sub x, right? If m sub y is equal to n sub x, then this is exact. That's what we check. Derivative dy. 2xy. This has no y's in it, it goes to 0. Derivative dx. You can check this for yourself, but taking the derivative dx, you get negative 2x here and negative y here, which gives you 2xy. And the cross partials are equal. Therefore, this is an exact equation. This is an exact equation. By the theorem, there must be some function f such that its partial dx is m and its partial dy is n, right? But if we take a look at f, this is difficult to integrate, dx, right? That's an annoying integral, dx. So instead, I'm going to start with n and integrate this dy, right? This is much easier to integrate dy than this is to integrate dx. That's exactly what we do. Integrating this dy, we get y squared over 2, right? And then we get y squared over 2. And then, like before, we get a functional constant of integration, except this time, instead of getting a function of y as the constant of integration, we get a function of x since we integrated dy, right? You get a constant of integration that's the other variable, right? Since we integrated dy, we get a function of x as the constant of integration. And I'm going to play the same game. I'm going to take this function. Now I'm going to differentiate it dx and compare that to m, right? If I take the derivative of this dx, I should get something that's equal to m, right? Something equal to m. Okay, so I take this derivative dx. Here I get xy squared, and over here I get 0, right? This has no x's in it, so I get a big fat 0. And then the derivative of h dx is h prime of x. And now I compare. Here's m, here's this. The xy squared is the same, so negative cosine sine should be h prime, right? Since this is m, h prime should be negative cosine x sine x. And it looks like we're going to have to integrate it anyways. I hope you remember how to do trig subs. This is one of the easier ones. You can use a u sub, right? When we integrate this dx, we integrate this dx. We can let u be cosine, and in that case, the derivative of, we can let u be negative cosine. That's even better. And the derivative of negative cosine is sine. So that gives us an easy integral here. Which means my function, right, if we go back up here, this is what f should have been. This is what f should have been. 1/2 x squared y squared minus 1/2 y squared plus h of y. And I just found h of y to be, h of x, excuse me. I just found h of x to be 1/2 cosine squared x, which means my f is 1/2 x squared y squared minus 1/2 y squared plus 1/2 cosine squared x. And therefore, the solutions to this look like this equals a constant, right? F equals a constant. F equals a constant. Normally, we'd be done, but since they gave us a initial condition at the beginning of the problem, we should solve for C, right? This says solve for C. This says solve for C. So we invoke our initial condition, right? Since y of 0 equals 2, I plug in x equals 0 and y equals 2 everywhere, right? I get 0, I get negative 4, and the cosine of 0 is 1. And that equals this constant. or whatever constant. Which means my constant here is 3. So therefore, the solutions to this initial value problem look like this. X squared plus x squared y squared, sorry, x squared y squared minus y squared plus cosine squared x equals 3. This is less important, but I'm going to show it to you anyway. Sometimes our differential equation is not exactly exact, right? It's not exactly exact, but maybe there's some other function mu which we can multiply through to make it exact. There's a whole way to do this. We're not going to go into details, but I'll just show you. Here's an equation in differential form. If we check the cross derivatives, right, if we check the cross partials, the derivative of this dy is 2x minus 2y, and the derivative of this dx is 2y minus 2x. This is not an exact equation. But if I multiply both sides by this factor, 1 over x squared y squared, sorry, 1 over x plus y all squared, excuse me. If I multiply both sides by this, it becomes exact. And I'm not going to show you the derivative. You can check it for yourself. Okay, so one more time. Let's talk about it. You have some function up here, right? In one direction, the dx direction, and the dy direction, you get m. And in this direction, you get n. And, whoops, well, that was annoying. If m sub y is equal to n sub x, that implies that's an exact equation. If that's the case, you can take f to be equal to the integral of m dx or the integral of n dy, right? You can take f to be this thing, one of these two things, and then you differentiate it, right? I guess here's the easy way to do it, right? Let's see here. What would you do? You could set n to be equal to partial y integral of m dx, right? You could set n to be equal to that. And then you could find the unknown function over here, right? Over here there'll be some g prime of y hanging around after you do that. And you can find that g prime of y that way. Okay.